Hello everybody. This is a quick lecture on the introduction to exponential and logarithmic functions. We'll start by going over some knowledge that you should have been exposed to in other classes, and then we'll make our way into things like graphing exponential functions, talking about some properties of the graph, and we'll move our way into logarithmic functions as well. So, without further ado, let's get started. All right, so something you should have seen in other classes are the laws of exponents. Now, each of the laws of exponents, if you will notice, always starts with the same base. The base meaning A. So, two numbers with the same base, they have different exponents. When you multiply them, you add your exponents. When you raise a power to a power, you multiply them. All right, and over here, if you have a negative exponent, that means you move the negative exponent in the numerator. That means you move it down to the denominator and make it positive. As well, anything to the 0 power is 1. All of these things you should have seen before. All right, so let's go over some of the basics. The 2 is called your base, and the 7 is called your exponent. Now this, again, not a vocabulary test. However, if I'm going to use these terms, I definitely want to make sure you know what I mean. So let's try a couple of problems. So here we have two problems. I have 6 to the 6th power times 6 to the 3rd power. Now the first thing you could do is multiply these out. However, it would be much easier to say I have the same base, so I'm going to add my exponents when I multiply. So I wind up with 6 to the 9th power. All right, again, n meaning any base, right? Same. So again, you're going to do it equals n to the 5 plus 7, which is n to the 12th power. All right, so let's take a look at the next one. Now over here, notice, how is this problem different? I have two numbers with different bases. Well, my exponent rules don't apply here. So this is just x to the 5th y squared, whereas over here, 41 squared, that could be a fairly high number, something you don't necessarily want to multiply out, especially when you're looking at 41 to the 7th power, and then multiplying those two numbers. So we wind up with 41 to the 2 plus 7, or 41 to the 9th power. And you could leave it just like that. When we divide our exponents, all right, again, the rule says that we subtract them. Now, let's take a look at y. So I have 7 times 7 times 7 times 7 times 7 over 7 times 7 times 7. And if I simplify my fraction, as I'm doing here, what do I wind up with? I wind up with 7 to the 2nd power. Same as if I would have said 7 to the 5 minus 3, or 7 to the 2nd power. So as you see, if you expand it and then you simplify your fraction, or you utilize the rule, either one is fine. As well, this would be x to the 10 minus 9, or x to the, not 5th power, excuse me, x to the 1st power. All right, so something that you should be aware of, but we're not necessarily covered too much in this class. 0 over 0. 0 over 0 is called an indeterminate form. It is indeterminate because if you were to make this into a equals n, make it into a equation, right? This would be equivalent to 0 equals 0n. And then the question is, what is n? Well, in this case, n could be anything we want it to be, right? Because anything times 0 is 0. That's why it's called indeterminate, all right? And there are some special things in calculus on how we deal with indeterminate forms. All right, so let's take a look at a quick application problem. In a light year, or the distance light travels in 1 year, is almost 10 to the 18th centimeters. To convert this number to kilometers, you must divide by 10 to the 5th. How many kilometers is in a light year? All right, so why don't you pause the video for a minute, try to work it out, and then we'll do it together. All right, so this one was a fairly straightforward problem. It said you had, that was in the pen, so 10 to the 18th centimeters, and we must divide by 10 to the 5th to convert to kilometers. So when we do that, we have 10 to the 18 minus 5, or 10 to the 13th power. And that would be how many kilometers in a light year? So 10 to the 13th kilometers per light year. And I do like to see my units when I give a word problem, so make sure you have them. All right, so let's talk about graphing exponential functions. Now, if we're talking about a function like 2 to the x, the first thing I would do is I would make a table of values. Now, your table of values will get very large very quickly. So I would hover right in the area between -2 and 2. All right, so when we take -2 and plug it in, we have 2 to the -2 power, or that would be 1/4. We plug in -1, I have 2 to the -1 power, which would be 1/2. If I plug in 0, I have, I have 2 to the 0 power, or 1. If I plug in 1, I have 2 to the 1st, or 2, and then 2 to the 2nd, or 4. All right, so now I'm going to have you pause the video. Why don't you try to plot these points, make a graph. All right, so I am going to erase because I have a table of values right here. And I do want you to notice, okay, I did -3 and I did -10 on my table, as well as 3 and 10. And notice my y values get very, very small and very, very large. That could be quite unwieldy, although they're not wrong values, but how in the world are you going to plot the point 10, 1024? Just doesn't seem realistic. But your graph should look something like this. And of course, we know that there are more points here, so you must have arrows on your graph. As well, notice here, we never go past y equals 0. So y equals 0 acts as an asymptote. So you got to put that in as well. Notice here, okay, the standard parent graph. All right, so let's take a look at what happens if we increase our base. So here I have a graph of 3 to the x and 6 to the x. And what happens as we increase our base? You can see that the graph gets steeper. All right, here we have 3 to the x and 6 to the x. And And what you can see from each of these graphs is that it indeed gets steeper. So we'll move on. All right. Some properties of the graph are here. I don't typically like when you just memorize properties. I kind of want you to get a feel for them. But the domain is the set of all real numbers. Now, how do we know the domain is all real numbers? There are no breaks in this graph. There are no discontinuities. There's no jumps. All right. Now, as we said, y equals 0 acts as an asymptote. Therefore, we could say there are no x-intercepts. An x-intercept, you might remember, is where this graph would cross the x-axis. Since it never crosses, there is no x-intercept. The y-intercept is at 1. All right, number 3 again, we're talking about the asymptote. And again, number 6 goes with number 1. The graph is smooth and continuous, so the domain is the set of all real numbers. All right, so what happens if we change our base to 1/2, to the 1/2 power? So I'd like you to pause the graph. I've given you a table of values already. Pause the video, given you a table of values. Why don't you go ahead and make that graph? Okay, once again, I would definitely recommend focusing between -2 and +2. That's enough points to get a good shape. That's what I'm looking for. And again, if we look here at even just 10 and -10, we're getting extremely large and extremely small numbers. So your graph should look something like this. Now notice I've labeled each point, so you can see if you went wrong where it was. But notice we still have an asymptote at y equals 0. However, what's the different about this particular shape? It's going the opposite direction. So let's move one slide forward. We notice here that this is going, right, we'll call this a J shape, kind of looks like a J. And over here we'll call this a reverse J. So by doing the reciprocal of your base, it changes the shape of your graph from J to reverse J, or back again. All right, and over here, I have some properties of those of the graph. Again, I'm never in favor of memorizing these properties. I'd love for you to be able to recognize them just from the graph. All right, again, 1 and 6 go together. Because the graph is smooth and continuous, we can call it the set of all, we can call the domain the set of all real numbers. All right, number 2 goes with number 3, right? Because the graph never crosses the x-axis, there is no x-intercept, and y equals 0 would have to be the asymptote then. So a lot of these properties can be deduced just by reading the graph. All right, so here's a pretty straightforward problem. I'd love for you to take a read. Graph f of x equals 2 to the -x minus 3. Determine the domain, range, and horizontal asymptote. All right, so what I'm going to do is I'm going to give you what I would consider the parent graph, which is 2 to the x. And I'd like you to pause the video right now for about a minute or two. And I'd like you to try to use transformations. Now, we talked about transformations earlier. Let's try to use some of those transformation skills to try to figure out what our graph now looks like. All right, so hopefully you paused the video and took a stroke at the graph. If you'll notice in my parent graph, I gave you the points. This hopefully made it a little bit easier to do the transformations. Now, the first thing that I noticed was up here, okay, from 2 to the x to 2 to the -x, right? I could also rewrite that as 2 to the negative 1 raised to the x power, or 1/2 raised to the x power. Now, what happened when I changed my base from 2 to its reciprocal 1/2? The shape changed from a j to a negative j. So let me take this away. All right, and what we notice is that this will actually be reflected over the y-axis. So it'll go from 3, 8 to 3, -8. And this will go from 2, 4 to 2, -4. So go from 1, 2 to -1, 2, and so on and so forth. Now the second transformation is a little bit more straightforward. When we subtract 3 from our function, what we notice is our function goes down 3 units. But I want you to notice my asymptote goes from y equals 0 to y equals -3, so everything goes down 3 units, including the asymptote. All right. Now let's take a look at the next problem. The graph f of x equals -e to the x minus 3 power. Determine the domain, range, and horizontal asymptote. All right. So again, I'm going to give you the parent graph. Now the reason, again, I'm giving you the parent graph, e is not a whole number. So notice I labeled some points. I'd love for you to pause the graph and take a stroke at utilizing transformations in an effort to make the new graph. All right, hopefully you paused the video and took a stroke at the next graph. So the first thing I want to take a look at is I want to know where my transformations are coming into play. All right, so the first transformation is that negative in front of the e. And what did we say that negative in front of the e does? As we see from the next graph, it reflects my graph over the x-axis. So for example, 2, 7.39, 2, -7.39. 1, 2.72, 1, -2.72, and so forth. Now the -3 here, the question is, what does that do? Well, that's going to act on this interim, this second graph, and we said it moves it 3 to the right. So when we move it 3 to the right, 1, -2.72 winds up being 3 to the right, 4, -2.72. And 0, -1 winds up being 3, -1. So we see that if we have the points labeled, it makes things much, much easier if we know our transformations. So the graph over here, this is your final answer. Now, a second option for this would be that if you wanted to, you could always make a table of values. However, in this case, the table of values would be increasingly difficult. So definitely know your rules of transformations. It'll make things a whole lot easier. All right, so at this point, I'm going to end this particular video. I like to keep my videos short and sweet. This is just an introduction to exponential functions. My next video, we will pick up where we left off, and we'll do an introduction to logarithmic functions. All right, so hope you enjoyed reviewing the video, and I will see you soon.